we start to solve this equation using series. Pxy double prime plus qxy prime plus rxy is 0. Suppose x0 is a regular singular point of this of this equation. That is, px0 is 0 and qx0 and rx0 are not all 0. Okay, at least one of them is not 0. And also, this means x0 is a singular point, but we require that it to be a regular singular point. For simplicity, we can also assume that x0 is the origin, is 0. Okay, if x0 is not 0, the method is the same. Or you can make a change of independent variable, let it to be x minus x0. Then you can translate the singularity to be 0. So without loss of generality, we assume that x0 is 0. Now, x0 is regular singular point. The definition means that x minus x0 multiplied capital Q over capital P is analytic. But x0 is 0, therefore this is xqx over px. This will be denoted by x small px. So this is by the regularly singularity assumption, this is a power series. Okay, so x small px can be expanded by a power series of x. Similarly, x square qx, that is x square rx over px, can be expanded by a power series. That is, both this function and the xpx are analytic. This is precisely the meaning of the fact that x0 is a regular singular point. Okay, so we have, because x0 is regular singular point, we have these two power series expansion. Now we multiplying the equation, both sides of this equation, by x squared over px. Our equation will become this equation: x squared y double prime plus x small px y prime plus x squared qxy. You divided the px both sides and then multiply x squared to both sides. You will get this equation. Then we use the expansion here and here. Using the expansion, we obtained by the condition that x0 is a regular singular point. We see that x squared y double prime plus x. Here x px will replace by the power series p0 plus p1x plus the higher order term. Okay, and for the coefficient of y, that is x squared small qx, we also replace the coefficient by the power series. Okay, so we obtained this result. Now, ignoring the higher order term, in the coefficients, we only keep the first term, because we are studying the behavior of the equation near x0 equals 0. So when x is close to 0, the higher order term can be, it is reasonable to ignoring them. Okay, so then we obtain this equation: x squared y double prime plus p0 xy prime plus qxy is 0. And this equation is an Euler equation we just studied. Okay, so this is the corresponding Euler equation, which our equation, and this Euler equation can be considered as an approximation of our original equation. The property of its solution reflects the essential character property of our original equation. So if we don't want to solve the equation, but we want to find out some property of the solution, we can turn to this Euler equation. But our purpose is to solve the equation. Therefore, let's go forward to solve the equation 3. As we said before, because x0 is a singular point, this equation might not have an analytic solution. Therefore, to use the series to find a series solution, you could not assume that the solution is a power series. Okay, power series are always analytic. So you need to study. You need to find solution of a more general form. Okay. So we choose the form. We study whether the equation has a solution of this form. That is a power function multiplied an analytic function. Okay. So I remind you that this function y might not be analytic because our r here is not necessarily a non-negative integer. If r is a non-negative integer, this y is analytic. But for some equation, this r might not be integer, and the r might even be irrational or even negative. So this make this expression represent a large class of functions, not only the analytic one. Only when r is a non-negative integer, this y is analytic. Okay, so we want to see whether this equation has a solution of this form. If it has a solution of this form, we need to determine the r and the coefficients an, so that we can write the precise solution. Okay, so r is unknown and the coefficient an are also unknown. Okay, so we show you the method to do this by a concrete example, because it is not useful to discuss the general. It is not interesting to make a general discussion of this equation. So we use a concrete example. Suppose we want to solve this equation. This is a second order linear variable coefficient equation. Okay, which polynomial coefficients, all the coefficients of y and its derivatives are polynomials, and we solve this equation for x positive. Okay, so how to solve this equation? First, we need to find the singularity. Singular points is 0. Okay, and we check whether this 0 is a regular singular point. So we consider the x minus x0, that is x multiply q over p. Because the coefficients are polynomial, so to see whether the singular point is regular, we only need to see whether the limit exists and finite. So we consider the limit of the first function. So this function is x capital Q over capital P. We denote it by x small p. This is substituting capital P and capital Q into this expression. We see that this is minus a half. So as x, this is a constant, in fact. So as x goes to 0, this constant function has limit small p0, that is minus a half. Okay. Similarly, you need to consider x square qx, that is x square capital R over px. Okay. Then this is substituting the p and the r inside. You will see that this is half of 1 plus x. So as x goes to 0, the limit denoted by small q0 is a half. So this tells us that x0 is a regular singular point. Okay. So the corresponding Euler equation, since we have already computed p0 and q0, if you have p0, q0, you have the Euler equation. Okay. So we obtain the p0 and q0, therefore we get the Euler equation. So Euler equation is easy to solve, and you can solve this Euler equation, and the solution can be considered as approximate solution for our original equation. But we want to find the exact equation, not approximate one. Okay. So how to do? We try to find solution of this form. A power function multiply a power series, that is an analytic function. We try to find solution of this form. And so suppose solution is of this form, we need to substituting this solution inside the equation. we need to substituting this solution inside the equation. So we need to compute the derivative of this y, okay? But this y represented as a multiplication of a power function and power series. So if you taking derivative directly, you will apply the derivative law for multiplication. That is complicated. So we move the power function inside the sigma summation and then combine the power of x. So this y can be written in this way. Which this way, it is easier to compute the derivative. Okay. So the first order derivative is sigma an r plus n and then x r plus n minus 1. This is the first order derivative. And we can also compute the second order derivative. The second order derivative is to taking derivative term by term. Power series can be derivative. Power series can be differentiated term by term. Okay, so our y prime is obtained by differentiate term by term. We differentiate the sum of the power series, but we can instead compute the derivative of every term and then sum up. Okay, this is important. And also for the second order derivative, we apply this method again, and then we get this. This is the second order derivative. So we're substituting this into the equation. The equation is 0 equal to 2x squared y double prime minus xy prime plus 1 plus xy. So we're substituting the expression of y double prime and y prime and y inside. So for y double prime, we have x squared. Okay. So this is 2x squared, copy 2x squared. Then y double prime here. This is the y double prime we obtained here. Okay. Then minus x. This is y prime. This is the y prime. an r plus n, x r plus n minus 1. This is y prime. Then 1 plus xy. So 1 plus xy. Y is the series. Y is the series x r plus n. Okay. So we will simplify this expression. This seems very complicated. Firstly, we combine the first two summation. The first two summation here in the first summation, the power of x is r plus n minus 2, but there is an x square in front of the summation. So x square will raise the order of x to be r plus n. Okay. Similarly, for the second summation here, the power of x is r plus n minus 1, but there is an x in front of the summation. This x will raise the order of x, also raise to r plus n. So both the first two terms, the first two summation, the order for x is the power of x is r plus n. So we write x r plus n here, and then combine all the other coefficients. That is 2an r plus n minus 1, and then minus an r plus n. So we are here minus an r plus n. Where is this an come? The last term in the coefficient. We look at the last summation in the previous step. 1 plus x summation. So we use the 1. The x we will write separately. We use the 1. Therefore, this gives us an an x r plus n. That is the term corresponding to 1 in the last term is here. An x r plus n. And then the x term remains. The x term gives us the power of x to be r plus n plus 1. Okay, so an x r plus n is an x r plus n plus 1. So this is the computation. You need to be very careful, otherwise you will make mistake. And the computation is wrong. I have to go to the next page. So to continue this computation, I will copy this last line to the beginning of the next page. Okay, so I copy this.